I'm going to be talking about the decoding of the climate system and its secrets. And I want to begin by telling you what a pleasure it is to be back here to talk to you about this, because really what I'm going to be talking about is a consequence of the time that I spent here. You know, they say you are what you eat, but in fact, I say you are who you meet. And the people that I met here back in the late 70s and in the early 80s were very influential and actually launched my career in the direction that it has taken. And so while I don't blame anybody for what you're going to hear today, I certainly want to give credit to the influences that I received while I was here as a student. A little bit of an outline so that you know where we're going with this. I'm going to give you a little bit of background about what I do and why I do it. I'm going to talk about the scientific motivations. And these are going to be centered around some grand challenges in climate science, some of which are long-standing grand challenges, and some are very current and urgent grand challenges that we, I think, as a society need to address. I'm going to talk about some scientific approaches, giving a couple of examples of how these grand challenges have been addressed. And then I'm going to go on and spend about the second half of this talk talking to you about what I consider to be a provocative new idea that addresses one of the grand challenges in climate science. It's a hypothesis that is being tested, and so the ideas that I'm going to be presenting to you are very much in a state of development, okay? So keep that in mind as we go through this, and if I see anybody going, oh my God, I like that, I'll know that we're on the right track. And then if time allows, I'm going to talk a little bit about future challenges and also opportunities that I think exist for a broader community effort in climate science. Okay, so I start out with a picture of planet Earth, and it's the water planet, of course. Everybody knows that, but what's particularly, I think, important for us to remind ourselves of is that it's a very special condition. The fact that the Earth is covered with water, 70% of it is liquid water, and a relatively small percentage of it is made up of solid water, ice, if you will. And it's a remarkable success story that the planet Earth has, for the better part of 4.5 billion years, been covered with liquid water. And it's important to keep that in mind because we know that just relatively small changes in the percentage of solid versus liquid water have a dramatic impact on the environment of planet Earth. In fact, in the last 50 years, over the course of my lifetime, the human population of the planet has doubled. It's now about 7.5 billion people. And about three-quarters of a billion people, or 10%, live within 5 meters of sea level, which makes them very vulnerable to very small changes in the percentage of solid water. In other words, changes in sea level. And in fact, we know from a geological standpoint that changes in the percentage of solid to liquid water can happen very rapidly. 19,000 years ago, for example, sea level rose 15 meters within just 500 years. So given the fact that our society is very much vulnerable to sea level variations, it's apropos for us to consider what is it about planet Earth that has allowed it to maintain a liquid surface, but also what has modulated that surface by changing the percentage of solid ice. So here's the challenge. The challenge is that the Earth receives most of its energy from the sun at low latitudes near the equator, and there's a net deficit of energy at high latitudes. So in order for the Earth to not become too warm at the equator and too cold at the poles, the Earth has to in some way transfer that energy between the low latitudes and the high latitudes. And the question is, you know, how well does it do it, and does it do it the same way through all time? And the fact is it's done by moving mass and energy, which is mostly, of course, in the form of water. But it turns out that geologists for a long time have known that the condition that we are familiar with today is not necessarily one that has characterized all of Earth's history. In fact, in the middle part of the 19th century, Louis Agassiz looked at the surrounding landscapes and puzzled over how these U-shaped valleys, or these scour marks that were exposed on the surface, could have come about. And he postulated that at some point in the Earth's past, there must have been a major glaciation that carved out these valleys and left behind these large striations, these scratch marks, if you will. That was, of course, followed by James Kroll, who picked up on the idea of glaciation and used the formulas that had been developed by Lowell to predict the planet Neptune. But he used these formulas to calculate Earth's orbital variations and suggested that the changes in Earth's eccentricity or ellipticalness of the Earth's orbit would affect the amount of winter season solar insolation and thereby affect the amount of snow that accumulates. And he predicted that that would have caused these glaciations. That, of course, was then followed up by others, including Milutin Milankovitch, at the turn of the century, who proposed that, in fact, it was Earth's obliquity cycle that would more strongly influence the seasonality, the solar insolation during summer, he suggested, and affect the amount of snow that melts during the summer season. Well, these geologists and engineers were largely poo-pooed by the real climate scientists of the day and disregarded. So it wasn't really until the turn of the next century, in the middle part of the century, particularly with the advent of World War II, that new types of technologies and explorations were begun, mostly in support of the war effort. They included the development of weather stations globally, and the first deep sea explorations were undertaken, mostly again for the purposes of defense and strategic development, but it led to the sampling of the seafloor that had not been done systematically before. And with that, of course, came new insights about the Earth that lay beneath that liquid surface. It also included major advances in nuclear chemistry, of course. The program started at Columbia in the support of the war effort, and that led to our understanding of the uranium series and stable isotope systematics, which provide a foundation against which to reconstruct this history of Earth's climate variability. And here's one of the first efforts to do that. This is a diagram taken from Cesare Emiliani's early paper on the oxygen isotope variability recorded in the shells of microfossils that have been deposited in the bottom of the ocean over time. And working with Harold Urey at the University of Chicago, they worked out the systematics of the separation of the heavy and the light isotopes of oxygen and how that would vary with temperature. And they then applied this methodology to these fossil shells collected from a core in the Caribbean. And Emiliani reconstructed this history of variability that was interpreted to reflect changes in sea surface temperatures near the tropics. And what you see from this diagram is that that reconstruction led to the notion that the Earth's temperature, the tropical sea surface temperatures, had undergone variations on the scale of 10 degrees centigrade, an enormous change in temperatures over a relatively short amount of time. Well, that was a breakthrough observation, but of course it was a very provocative one because climate scientists at the time were not willing to accept the notion that the Earth's climate could undergo such extreme climate changes, and certainly not on the timescales that Emiliani was suggesting here. And of course that led to a lot of additional science that refined our understanding of what those oxygen isotope records actually mean, of course, and then we now understand that those variations are primarily a reflection of the change in the oxygen isotope composition of the ocean as a result of the buildup of ice on land. Nonetheless, those records still stand as a document of the variations in the Earth's climate system that have taken place over the course of the recent past. And it is against that backdrop that we now look at the modern day manifestation of changes in the Earth's energy budget. This is a reflection of this is a record, if you will, of the Earth's average mean surface temperature over the 20th century as it is now composited from weather stations and the like from all over the planet. And you can see that from this diagram that the Earth has been warming by about a degree over the course of the 20th century. So even to a casual observer, not familiar with the Earth's long history of climate variability or a climate dynamicist understanding the Earth's energy budget, even a casual observer can look at that and see that something is changing. This on the right is a map that illustrates where those climate changes are having the most profound impact. And this is an anomaly map, so these colors represent the difference in mean surface temperature at various locations across the surface of the planet relative to the mid-century, 1951 to 1980. So in the bottom, you're looking at the surface anomaly or temperature anomaly in 1905 at the beginning of the 20th century, and at the surface is last month's surface temperature anomaly. And then you can clearly see that the temperature changes have been most pronounced at high latitudes. The dramatic changes that are taking place at high northern latitudes particularly stand out in this diagram. So the question is, then, what happens to the climate system overall as a consequence of these climatic changes that are taking place over the surface of our planet? Recognizing that the Earth's energy balance is no longer balanced, the World Climate Research Program has put forth several grand challenges that need to be addressed in order to understand or anticipate how the climate system, our environment, will respond to that imbalance in the Earth's energy budget. It includes understanding how cloud circulation and climate sensitivity will change. And in particular, it includes effects on water availability. Now, water availability is not a big issue here in Ohio, but believe me, it's a big issue in California, where I come from. And unfortunately, to understand how water availability will be affected by the change in the Earth's energy budget, we have a relatively short instrumental record against which to test ideas or to test hypotheses or model simulations, if you will. And so we need longer records in order to ask questions about how the water availability will be affected as this energy budget changes. So for the last 5 years, I've been funded to lead, as Lonnie pointed out, an interdisciplinary, inter-institute endeavor to try and expand our understanding, if not solve the question about how water availability in the western United States will be affected by changes in the Earth's climate. We've been funded by NOAA, NASA, and the National Science Foundation, and we're just scratching the surface. And scratching the surface means it is such a complicated problem that it will take a very long time for us to get to the point where we can accurately and with confidence predict how water availability will be affected in the western U.S. as the climate continues to warm. So with that, I'm going to move on, and I'm going to talk instead today about another important grand challenge, and that is what happens to the solid form of water on our planet as the planet warms. What is the consequences of ice melting to the Earth environment? Now, so I'm going to give you just a little bit of background to give you a sense of where I come from and how I approach or how I come to this grand challenge. And for me, it began back in the late 1970s as an undergraduate student here at Ohio State, and I took my very first class in geology from George Moore, who at the time was talking to a bunch of bright-eyed, starry-eyed kids about how mountains are built. And he put forth the two competing hypotheses at the time of the so-called seafloor spreading hypothesis and this other radical idea called the shrinking apple theory. I was fascinated. I was drawn in by the notion that geologists could ask these kinds of questions about planet Earth. And so I became a geology major as a consequence of that class and, of course, the subsequent classes that I took. But I owe a lot to George Moore and that very stimulating lecture that he gave and convinced me to become a geologist. I went on to work with colleagues and other students in the Institute of Polar Studies, as it was known then. And I was very fortunate to have had the opportunity to work with Peter Webb as a graduate student. Bill Zinsmeister and Tom DeVries kindly invited me to go on expeditions to southern Chile and to look at exposures of Pliocene marine sediments exposed in the fjords of southern Chile. And perhaps as important as any other event in my time here at USC, I became really close friends with John Mercer. For whatever reason, he and I got along really, really well. And I hung out with John Mercer and Judy, and he had a really profound impact on my interest in climate variability, and particularly high latitude climate variability. And in fact, that friendship really led to a very influential paper for me. He published this paper back in 1978. And he said in this paper that if the global consumption of fossil fuels continues to grow at its present rate, atmospheric CO2 content will double in 50 years. And he went on to say climate models at that time suggested the resultant greenhouse effect will greatly be magnified at high latitudes. And he said that could lead to a catastrophic collapse of the West Antarctic ice sheet and give rise to a 5-meter rise in global sea level. Well, this, of course, as probably most of you know, was a very, very provocative paper at the time. And a lot of people were really resistant to the notion that the West Antarctic ice sheet could become unstable. But I think now in retrospect, it was a very, very compelling observation by John. In any event, he also came to this realization from his studies of ice sheet variability in the past. He had been studying the history of Antarctic ice sheet variability, looking at rock and glacial tills deposited along the transantarctic mountains. And so he gave to Peter Webb's group a group of samples from the so-called Sirius Formation. And one of Peter's students, David Harwood, took from that sample marine diatoms that he had found and dated them. And these marine diatoms that David identified were of Pliocene age. And probably a lot of you know this story, but that led to a very, very provocative idea, and that was that these Pliocene sediments, these glacial sediments, were laid down at a time during the Pliocene when the Antarctic ice sheet had undergone a very rapid and dramatic retreat. And so that led to a proposal that took me and David Harwood and several other people to Antarctica to resample those collections and to do a much more thorough investigation of what the age of these sediments are, and indeed, was it really a manifestation of the instability of the Antarctic ice sheet. So here I am in 1983. This is one of the cairns left behind by the Stott expedition on its notorious attempt to reach the South Pole. And I also came across a boulder left behind with John Mercer's name scratched in it. So he left his mark on me, and I decided to leave my mark behind with his name. So this is one of the really important mementos in my intellectual development. In any event, as a consequence of that experience, I then became very interested in going on to pursue other climate questions, and I decided to go on and do a degree in oceanography, and I went to the Graduate School of Oceanography, where James Kennett had organized an expedition to go to the Southern Ocean here in the Weddell Sea and core through the sediments that had accumulated on the Maud Rise over the course of the Cenozoic. The first ever attempt to reconstruct or to collect a sediment record from the Southern Ocean that would extend through the last 60 million years of Earth's history. The goal of which, of course, was to reconstruct how the Southern Ocean and how the Antarctic continent's climate had varied over the course of that time. So I was given the task as a graduate student to reconstruct the isotopic record left behind in the shells of microfossils that were deposited in these sediments on Maud Rise. And this is a reconstruction, not the one that I generated, but it is very much like the one I generated. And on the left-hand side, you can see the oxygen isotope composition of these marine fossils. These are benthic fossils. These are benthic forams that inhabited the bottom of the ocean at this location. And on the right-hand side is the carbon isotope composition of the shells of these foraminifera. And just a brief look at this, you can tell the dramatic variations that have taken place over the course of the last 70 million years. If you translate these oxygen isotope values into temperature and into ice volume variations, as depicted here in the bottom with a temperature scale, you can see that the temperatures have undergone dramatic changes over the course of the Cenozoic. In fact, if you go back to the early part of the Cenozoic, the temperatures at the bottom of the ocean in the Southern Ocean were as warm as 12 degrees centigrade. 12 degrees centigrade. And over the course of the Cenozoic, they've dropped dramatically. Okay? And also superimposed on this long-term record are a series of dramatic events. There's a dramatic event you may not be able to see so well in this diagram right there. Okay? And it corresponds in time with another event in the carbon isotope composition of these shells. Okay? This is a major transition in Earth's biological history. This was the end of the marsupial, what do you want to call it, dominance of our planet, and the revolution, the placental revolution began. It's also, it turns out, a major extinction event in Earth's history. Most of the benthic organisms that were inhabiting the bottom of the ocean went extinct right at that time, right there. Well, that turns out to be what is now referred to as the PETM, or the Paleocene-Eocene Thermal Maximum Perturbation. And there it is in the core. Okay, that's what it looked like when the core was brought up on deck, and we broke it open, and we saw, we didn't of course know at that time it was the Paleocene-Eocene boundary, but that horizon stood out dramatically against the backdrop of this otherwise rather, nondescript marine sediment. Okay? But in close examination of the sediments right at that horizon, we found that's where the extinction took place. And it also turns out that the reason why those sediments are brown is because there's very little carbonate left. In fact, this is a major carbonate dissolution event. So in addition to the extinction itself, the oceans became highly acidic and the calcium carbonate dissolved. So we've gone on then to investigate this even further, and it turns out that there is a major change in the oxygen isotope composition and the carbon isotope composition of these shells. Now, it's an interesting story for me to relate to you because, again, this was back in the early 80s when a lot of this kind of information was not previously seen. These long records of Cenozoic oxygen isotope variability had not been produced. Okay? So we didn't have a context against which to understand what these kind of excursions actually represent. So I was working on the reconstruction of this record, and I remember going into the lab and seeing these results and just thinking, well, this can't be right. So I actually went back and reran the samples again, and the samples came out exactly the same. So I took these results to Professor Kennett, my advisor, and I showed him. He said, oh, something must be wrong. Go back and redo this. And I did. I went back and I reproduced them yet again. And each time it came back with the same answer. So it was very clear that this was a robust record of something happening in the ocean. Okay? We didn't know what, but clearly a dramatic change in both temperature and carbon isotope composition. Now, it turns out that subsequently, people have looked at this in even more detail. So let me explain to you what you see here on the right-hand side. This is zooming in on this little horizon right there in the core. Okay? And each one of these little single symbols represents an individual fossil shell, a microfossil shell of either a planktic foraminifera, that is an organism that inhabited the surface ocean, or a benthic fossil, one that inhabited the bottom of the ocean. And if you look at this diagram here on the left, you can see that the transition in the measurement of these individual shells is dramatic. Okay? Within a centimeter of the core, the values jumped, I should say, by over a per mil. Okay? A per mil. And if you look closely on the right-hand side, you can see similarly in the carbon isotope composition, there's a similarly rapid, large jump in the carbon isotope values. And in fact, when we analyze these individuals, if you can zoom your eye in on this little region right here, there appears to be no individuals with values in between these and those, implying that for all intents and purposes, this carbon isotope perturbation happened instantaneously, at least geologically. These little fossils only live for weeks at a time. Okay? So whereas there appears to be a little bit of a transition in the oxygen isotope composition, the carbon jumps immediately. Now, importantly for this story, you have to remember that it appears that the oxygen isotope change is a reflection of temperature, primarily. And it appears from this record that the temperatures began to warm slightly before, but not too long before, the carbon isotope excursion takes place. Okay, so they warm, and then suddenly the carbon isotope changes. Okay, well, this was a major challenge to explain, and subsequent to these observations, people put forth the hypothesis that the carbon must have come from a very highly carbon 13 depleted source. Okay, that being something like methane, which has a very depleted carbon isotopic signature. And the release of methane as a greenhouse gas would have contributed to this abrupt warming. But importantly, the thing to remember is that the temperature changed first, or began to change first, and then the perturbation happened. And that will become important as I go through the rest of this talk, okay? So very large carbon perturbation caused in some way by this temperature change. Well, so just this last week, Richard Zeeby and his group have used a series of really innovative climate Earth system models, models that not only simulate the dynamics of the ocean itself, but also simulate the biogeochemical cycling within the ocean. And they applied some very clever time series analysis to try and get at just how rapidly the signal must have been propagated throughout the ocean in order for it to be recorded in the shells of these bottom-dwelling organisms, okay? I won't give you the gory details of it, but the bottom line is that what they come out with this study with is the conclusion that this event at the Paleocene-Eocene boundary must have entailed a release of carbon on the scale of between 2.5 and 4.5 thousand petagrams of carbon, okay? And the temperature change that led the carbon perturbation must have been something on the order of between 50 and 100 years. 50 and 100 years, and then a perturbation with a magnitude of that scale. That should be a really important thing for everybody to recognize, because that scales to something like 0.6 to 1.1 petagrams of carbon being released to the environment each year over the course of about 4,000 years. Okay, that's what it took, that much carbon, to produce an excursion in carbon and the associated climate changes associated with it. Okay, why is that important? Because this is the current carbon perturbation taking place today. Okay, this is the record from Mauna Loa of the change in the atmospheric composition of CO2, and it has now reached approximately 400 ppm. Okay, and it has done so at a rate of 10 petagrams of carbon per year. So 10 times faster than the Paleocene-Eocene boundary. Take that in. 10 times faster than that catastrophic event at the Paleocene-Eocene boundary. So Zeeby et al. Wrote this in their paper. They said, we are now entering what they call a no analog state, representing a fundamental challenge to us to put constraints on where our climate system is going to go as a consequence of this no analog rate of carbon release. And importantly, they point out that this will have dramatic consequences to the ecosystem of our planet. At the Paleocene-Eocene boundary, it wiped out most of the marsupial mammals. It took out most of the bottom-dwelling organisms in the ocean, and the ocean became acidified. Okay? And we are looking at something much grander in scale taking place today. Okay, so with that backdrop, the question, the grand challenge that I'm proposing or I'm putting forth to you today is, how will the climate system respond to this current carbon perturbation? That's the grand challenge. So how do we get at that challenge? Well, it's not going to be easy. It's certainly not easy today, but we have some hope by looking at some of the archives that entail periods in Earth's recent past where there have also been carbon perturbations, where we can access the types of information necessary to break the code and understand how the climate system responds to a perturbation in the carbon cycle, in the carbon system. Now, of course, these are natural perturbations. These weren't caused by humans, but this record is a record of the concentration of atmospheric CO2 extracted from the bubbles left behind in ice cores from Antarctica. I'm sure most of you are familiar with this, but superimposed on this black atmospheric CO2 record is Antarctic temperatures. Okay, and the takeaway message from this is that the temperatures at high southern latitudes have varied in close association with these carbon perturbations over the course of the last at least in this diagram, over the last 800,000 years. Okay? Now, what does this record tell us? It tells us that there have been 9 natural perturbations in the carbon system over the last million years. But importantly, the perturbations have happened abruptly. Okay? So each one of these perturbations marks the termination of one of the ice ages during the late Pleistocene. And if we look at this diagram in close detail, what we can recognize is that there is a lead-lag relationship between temperature at high southern latitudes and those carbon perturbations, just as there was at the Paleocene-Eocene boundary. So with this backdrop, scientists have worked for the last 30 or so years to try and understand what is it about the climate system, what is it about the Earth system that can so systematically constrain or control the concentration of atmospheric CO2, keeping it within this narrow range of 180 and 280 parts per thousand. Okay? What is it in the climate system, the carbon budget, the carbon cycle that can regulate it so systematically? Well, simple thermodynamics doesn't work. People have attempted to explain it on the basis of changes in carbon export and the carbonate compensation depth in the ocean. It doesn't work. Turn to the biological pump, the uptake of carbon by phytoplankton in the ocean and the sequestration of that carbon into the deep sea. Lots of problems with this hypothesis. It just doesn't seem to explain the observations in detail. And so the canonical idea that most paleoclimatologists are working on right now is the notion that somehow the deep ocean becomes so stratified, the bottom of the ocean becomes so stratified that it acts as an isolation reservoir, so that the carbon that gets taken up by phytoplankton in the surface ocean then accumulates that carbon as that particulate matter falls down to the bottom of the ocean. And then somehow that reservoir gets then reventilated at the end of the ice age abruptly, and that CO2 is released to the ocean atmosphere system. That's the working hypothesis as of today in the paleoclimate community. The problem with that is that no one has been able to fingerprint that reservoir. International efforts spend millions of dollars going out and trying to find evidence, trying to find where that reservoir exists or existed in the ocean, and they ain't found it yet. Nonetheless, it continues to be the accepted idea to explain these systematic variations in atmospheric CO2. So I ask, is there something else that we're actually missing? And the reason I come to this question has a lot to do with some discoveries that have been made not just by climate or oceanographers, but by people working in other fields. And this is a key, I think, for unlocking some of the secrets to the climate system. Drawing upon information that is being developed by other disciplines. So the question then, the grand challenge associated with this is what happens in the Southern Ocean? Okay, the Southern Ocean is tied to Antarctic temperatures, and the Antarctic temperatures are closely coupled to those variations in atmospheric CO2. So understanding what happens in the Southern Ocean is key to understanding what happens to the carbon in the ocean. And the question is, does the Southern Ocean take up more CO2 as the temperature starts to rise? Okay, that's one possibility. Or does the Southern Ocean become a larger source of CO2 and become a positive feedback? In other words, As the ocean warms, the Southern Ocean warms, what happens to the ventilation of CO2 from the ocean, and what happens to the uptake of CO2 in the Southern Ocean? That balance between those two acts as a regulator, if you will, of the CO2 exchange between the ocean and the atmosphere. Well, the modern oceanographers are struggling to answer this very question. And we don't yet know the complete answer, but we have some important new observations that shed light on this. This is a recent article by Hoffman et al. And one of the interesting things that they've discovered is that despite the warming that is taking place on the planet today, sea ice around the southern continent is actually expanding. And with that expansion of sea ice has come a change in the hydrologic balance of the Southern Ocean. And they've done the careful calculations to point out that the expansion of sea ice is leading to a dilution, a lessening of the salinity of the surface layer in the Southern Ocean. Okay? And that has a couple of important consequences. One is that it increases the stratification of the surface ocean, reduces the amount of convection or ventilation of carbon coming up from below. The other thing that it does is that it increases the salinity of the waters that are forming deep water, bottom water, off the shelf. Okay? So enhancing the subduction of deep water in the Southern Ocean. It's somewhat counterintuitive because the climate models that we have today predict just the opposite should happen. I don't have time to give you all the details, but the canonical notion is that as the Antarctic warms, the sea ice should retreat. Okay? And the amount of ventilation should increase. Well, it doesn't seem to fit the observations. And so it's a question that has to be addressed if we're going to understand what happens in the future in the Southern Ocean. And as I point out, there are contrasting implications to this lessening of salinity. Summer season warming leads to enhanced freshwater forcing of the sea ice and causes greater Southern Ocean stratification. Winter season upwelling due to enhanced wind forcing is therefore reduced. Okay? Now, that then suggests, based on these observations alone, that the Southern Ocean, under these circumstances, should become a greater carbon sink as the Earth warms. Okay? And negative feedback on this perturbation. However, the glacial terminations are just the opposite. They suggest that PCO2 was rising as the Southern Ocean was warming. So what's the story? What's the answer, if you will, the contrasting implications to this observation against a backdrop of those 9 perturbations that have punctuated Earth's history over the last 800,000 years? Well, again, I'll come back to this timing and pointing out it's critical to understand the timing and the rates of change. So this is a record of the atmospheric CO2 concentration recovered from an ice core in Antarctica, and it shows the deglacial history of atmospheric CO2 at the end of the last ice age. So you can see it starts to rise at about 17.5 kiloyears BP. And if you look at this record up here, this is the corresponding change in Antarctic air temperatures, reconstructed again from the ice cores. And there is approximately 800-year lead to temperature relative to the CO2. Okay, so what's the takeaway from that? Antarctic temperatures started to warm before the greenhouse gases rose in the atmosphere. That's a very important observation to keep in mind. Okay, so what role then does the Southern Ocean actually play in regulating the concentration of atmospheric CO2 during one of these perturbations? Key fundamental question to be addressed. Well, there are some important clues, and this is where now I'm going to start venturing into a new provocative idea. Okay, so one of the clues that we have comes from the record of radiocarbon. This is a reconstruction of radiocarbon in the atmosphere over the last glacial termination. And you can see from this reconstruction that as the concentration of atmospheric CO2 was beginning to rise in the atmosphere, the radiocarbon content was dropping. And in particular, it dropped very rapidly right here in this interval of time, just as atmospheric CO2 was starting to rise. Okay? Now, we have a variety of different ways to try and ask what controls that radiocarbon variability, and one of the controls on that variability is what the production rate of radiocarbon is in the atmosphere. And we can approach this by using other isotope methods I don't have time to really talk about right now, but the bottom line is that those records tell us that that rate of decline in the amount of radiocarbon in the atmosphere cannot be explained by changes in the production of radiocarbon, and therefore must reflect an input of radiocarbon depleted carbon into the system, into the Earth system. Okay? And it's been termed the mystery interval. So where did this carbon come from, in other words? Okay? So that's clue number one. A very highly depleted radiocarbon source entered the system as atmospheric CO2 was beginning to rise. So if it wasn't radiocarbon production, then how much carbon must have been added to the system, and what must its radiocarbon content have been in order to explain that 190 per mil drop? Well, it can take a very simple back-of-the-envelope mass balance approach to this and simply ask, okay, if the carbon entering the system was all of that radiocarbon change was due to an input of radiocarbon depleted carbon, how much would be required to explain that 55 ppm rise in atmospheric CO2? Okay? Solving this very simple mass balance calculation says that the carbon content of that source must have been about minus 641 per mil. Okay? What does that mean? It means that the source, if it was entirely from one single source, it means that source was virtually radiocarbon dead. So dead carbon has a carbon content of minus 1,000, right, in these units. And so this carbon was very close to being radiocarbon dead. In other words, really, really old. Okay? Much older than the carbon that accumulates in the bottom of the ocean as phytoplankton die and settle down to the bottom of the seafloor. Okay? So, if most of it is dead, where the heck did it come from? Well, again, another clue has come about as a consequence of measuring the radiocarbon ages of those shells of benthic forams that have accumulated on the seafloor, in this case at a site right off the coast of Baja, right here. Okay? And the reconstruction of their radiocarbon content is shown in this diagram right here in black. And it's plotted against a backdrop of the change in concentration of atmospheric CO2 and the drop in radiocarbon content of the atmosphere. So there's that very rapid drop I just pointed to, the so-called mystery interval. And lo and behold, this site here off the coast of Baja documents a dramatic excursion in radiocarbon. Okay? Now, these authors back in 2007 puzzled over this and suggested that it must represent the ventilation of carbon from somewhere deep in the ocean that entered the upper ocean and then made its way all the way to the coast of Baja. One possibility, but it turns out that that's a really hard way to explain this. And in particular, we came along later and reconstructed the radiocarbon content in sites right here off the coast of Galapagos, and we found that the excursion was even far larger than the one off the coast of Baja. Okay? So old, in fact, that if you translate these into age, it suggests that the age of the water in which these forams were living was something like 6,000 to 7,000 years old. Okay? Really unrealistic kinds of radiocarbon ages, and therefore it was clear to me very early on that this could not be a manifestation of the ventilation of deep water from somewhere in the ocean. Now, the next important clue, I've got to go through this quickly because I've only got a couple minutes of time to make through this, but the next clue came about again by geologists and biologists working on completely independent topics, looking at a new discovery that had been made in the ocean. So watch this video with me for just a second. This is in the back arc basin of the Okinawa Trough in the Western Pacific. It's in about 1,000 meters of water, okay? And they're taking a submersible down, a remotely operated submersible. And this is the seafloor you're looking at here. And you can see how quiet it is, okay? Watch what happens when they stick this probe into the sediment surface. You know what that is? Take a guess. Nope, it's not methane. It turns out it's liquid CO2. Liquid CO2. And in fact, it's referred to as a lake because there's so much liquid CO2 trapped within these sediments. Now, how does it get trapped? Well, it's an interesting story, one that would require a whole lecture to talk about, but the bottom line is that it turns out that liquid CO2 exists in the ocean today at temperatures cold enough, okay, and at pressures high enough for the CO2 to liquefy. And they're stored in the sediments that blanket the margins of hydrothermal sites in the ocean. And it's kept within the sediments by a thin layer of solid CO2 or hydrate CO2. Okay? So this is, again, another location studied in the ocean, but it illustrates to you how the CO2 forms. It is a result of the outgassing of these hydrothermal systems, and seawater passing through these hydrothermal sites flushes the CO2, and this CO2 then diffuses into the sediments and accumulates beneath a layer of hydrate until something comes along like that probe and disturbs it and releases that CO2. So these observations, these three observations that I've just given you, led to a new and very provocative hypothesis that we published in 2011 that suggests that the link between temperatures at high southern latitudes and the variations in atmospheric CO2 are a result of changes in the stability of hydrate and liquid CO2 in the ocean that accompany those temperature variations. And here's how it works. Basically, well, let me first point out that if this hypothesis is true, it has some constraints on it. It must explain the timing and the magnitude of those recurrent perturbations that I talked about, and it has to account for the drop in radiocarbon that I illustrated to you. So those are two requirements that must be met for this hypothesis to be validated. So first of all, as I said, the stability of hydrate and liquid CO2 is both temperature and pressure or depth dependent. So here's the profile of temperature through the ocean today. And you can see from this three-phase stability diagram that liquid CO2 is stable in the ocean today at temperatures, above 9 degrees at depths below 400 meters. Okay? And the solid form of hydrate is stable at temperatures below 9 degrees and at pressures somewhere below, at higher pressures below 400 meters, okay? But during the glacial, it turns out, the temperatures in the ocean were colder, okay? And so this is a temperature profile reconstructed for the glacial ocean. What you can see is that the stability of hydrate in the ocean shifted upwards in the ocean by as much as 300 meters. Okay? So consequently, when you map that temperature change in the ocean and translate that into how the stability horizon for hydrate would have changed in the ocean, this is what it looks like. These are contours of how much shoaling would have taken place in that hydrate horizon. And you can see that in much of the Pacific Ocean, that hydrate horizon would have shoaled by as much as 250 meters. And importantly, those regions where it shoaled are today associated with active hydrothermal venting. So this is a map of what are currently known about hydrothermal sites in the Pacific, well, around the global ocean. So these red dots represent known active hydrothermal sites. The yellow dots represent assumed, unconfirmed hydrothermal sites. And you can see how widespread they are. And shown in these red circles are the places where those carbon-14 excursions have so far been documented. And they correspond to locations where there's active hydrothermal venting today. Okay, so the conceptual model is as follows. We hypothesize that during glaciations, as the ocean cools, the hydrate horizon shoals upward, and consequently the area over which liquid CO2 can accumulate within the sediments, the blank of these hydrothermal sites, would have expanded, okay, and trapping CO2, keeping it from going into the ocean system. And then during those rapid perturbations, the ocean warms and triggers a release, a destabilization of that hydrate. And the liquid CO2 that had been stored within the sediments then is released to the ocean and ventilates to the atmosphere. That's the conceptual model. Now, the other important part of this is that, as I said, if this hypothesis is correct, it means that the temperatures in the Southern Ocean have to warm first. That's the trigger in order to release this CO2. So the requirement is that there must have been a temperature warming before the carbon perturbation, and in fact, that's exactly what we see. So here, again, this is a paper I published a few years ago. This is a temperature reconstruction. It's an oxygen isotope record, but interpreted in this case as a reflection of temperature, okay? There are two temperature excursions that happen on the scale of about 2 degrees centigrade before the carbon isotope and before the rise in atmospheric CO2 occurs. Okay? So the magnitude of temperature change and the timing of temperature change are just right to explain the destabilization of hydrate in the ocean and the consequential release of this liquid CO2 to the ocean and atmosphere. Okay, by way of this, so this is how it works basically. This temperature signal from the Southern Ocean is propagated at intermediate water depths to those sites where those hydrates have been forming. Okay, so where do we go from here? Well, to test this hypothesis now, we've got to do a number of different things. And we have to ask, does the amount of radiocarbon dead required to explain this radiocarbon excursion agree with the atmospheric record? Okay, that's one thing we have to do. Then an injection of carbon at intermediate water depths would lead to acidification, just as it did at the PETM. So is there evidence of a change in carbonate ion concentration in the ocean? Is there ocean acidification at sites of release? And then, is there a trace element signal associated with it? If this is carbon, CO2, coming from hydrothermal systems, it will carry with it hydrothermal geochemistry, chemical fingerprints of hydrothermal emissions. Okay? So these are the three things that we're attempting to address. Now, to address number one, we're using a carbon system model. This is an Earth system model, again, like the one that Zeeby et al. Used, that is capable of simulating not only ocean circulation, ocean dynamics, but also the cycling of nutrients and elements in the ocean as well. And it does a very good job of simulating the ocean. So on the left-hand side is the modern-day distribution of constituents in the ocean today. This is a profile taken through the eastern South Pacific right here, okay? So these are profiles of phosphate, salinity, and radiocarbon recorded in observations. And on the right is the model-simulated version of those in the model. Okay? And all you have to do is kind of look at the colors to see that the model does a really good job of simulating the ocean's distribution of these constituents. So we have confidence in the model's ability to simulate ocean behavior and the cycling of elements. And when we use this model to ask a very simple question, how much radiocarbon must have been released in order to explain the magnitude of those radiocarbon excursions, it tells us that to get an excursion of the scale we see requires a release of carbon on the order of about 1,400 gigatons over the course of about 6,000 years. Okay? Again, a very important number to remember, 1,400 gigatons of carbon. Now, the other important thing about this picture is that you can see that the signal in radiocarbon is attenuated rapidly away from the site of release. And this is important because the arguments have been made that these radiocarbon anomalies must have been released from the deep ocean and then propagated through the long pathways of ocean circulation to these sites where these are recorded. And it just doesn't work. the signals are just diminished too rapidly away from the site of release. And so in order to get those excursions, as we see in the records, that had to be very local releases. A very important observation. Okay, and so does the model simulate the atmosphere, radiocarbon? Yes, it does. When you put that much carbon into the ocean to produce signals like those that we see in the record, it produces an atmospheric record of radiocarbon that matches the observations. That's important to testing the hypothesis. The second thing is that the release of carbon of this kind would also produce excursions and other things like the delta C13 of carbon in the ocean. So this is a reconstruction from Antarctic ice cores of the delta C13 of CO2 in the atmosphere during the last deglaciation. And you can see there's an excursion during the so-called mystery interval. Okay? Well, it turns out that you also see it in the marine sediment record. So this is reconstructed radiocarbon, delta C13 values of plankton, the little forams that had lived in the ocean during the last deglaciation. And they too record an excursion during the mystery interval. Now what's important about this is that the model, when you ask the model to simulate that radiocarbon excursion, it also simulates a delta C13 excursion. And it turns out that the pattern of the delta C13 excursion in both the ocean, the surface ocean, and its simulated atmosphere match the observations, both in timing and in scale. So it's clear that this mechanism matches the observations well. And then just a couple last slides. Going back to this issue about what role the Southern Ocean plays, and this dilemma that we have in the modern about whether or not the Southern Ocean is going to be a positive or a negative feedback. Well, in this example, in these perturbation experiments, it turns out that the model simulates a uptake of carbon by the Southern Ocean. So as sea ice retreats in this model, as the Southern Ocean warms, sea ice retreats and the Southern Ocean takes up more carbon, becomes a net sink for radiocarbon. This is just a plot to show you how the model simulates a reduction in sea ice around the Southern Ocean. Okay, so this then was really a very compelling result from the modeling, but then it turns out that some other scientists had measured a new method, or applied a new method to reconstruct the PCO2, or the change in PCO2 in the ocean during the last deglaciation using boron isotopes. And they found that this part of the Eastern Pacific, the same location where we had found the radiocarbon anomalies, was also associated with an anomaly in beryllium-11, interpreted to reflect a net increase in the flux of CO2 out of the ocean during the last deglaciation during the mystery interval. Consistent with the hypothesis. Okay, so there it is right there. Okay, now lastly, and then we'll be done, the model then also simulates the carbonate chemistry change. So you release that much CO2 to the ocean, it becomes acidic. It changes the carbonate ion content, and this is how the model simulates that. So this is the carbonate ion content of the surface ocean in the eastern equatorial Pacific. And so we looked for evidence of carbonate dissolution, and lo and behold, we found it. Okay? There's a dramatic drop in carbonate accumulation right at that carbon excursion. And if we look at this is the event right here. Okay? This is what it looks like under a microscope, or a SEM in this case. You can see the organisms are partially dissolved. Okay? So again, very consistent with the Paleocene-Eocene boundary, of course, but at a smaller magnitude. Okay, and then this is just to illustrate that there is also trace element fingerprints of hydrothermalism. So, for example, the copper to calcium ratios increase, and zinc also increases. These are elements associated with hydrothermal emissions. And then we asked the model, okay, so you've done a good job of simulating what happened in the ocean. What about the PCO2? Does it match the record of atmospheric CO2 that the ice cores record? And lo and behold, it does. So when you put that much carbon in the ocean at that location to match the observations, and then simply ask, what happens to the atmosphere? It turns out that the atmospheric record of CO2 matches the observations very, very well. So we think that we've turned a corner on this problem, on this grand challenge. What has controlled the concentration of atmospheric CO2 repeatedly over glacial interglacial timescales? We think we've turned the corner on this. Okay? It remains to be proven, but we think we're on our way to breaking through a new way of looking at ocean atmosphere climate dynamics. Okay, so this hypothesis reconciles the lack of evidence for that isolated deep water mass in the bottom of the ocean. During the last glaciation, the deep Pacific temperatures warmed and cooled in close correspondence with the Antarctic temperatures. That's key. So what happens in the Southern Ocean acts as a trigger for this mechanism. And these deep water temperatures changed large enough to have shifted the hydrate stability. The time required to propagate that temperature signal to those sites where hydrate accumulate explains the lag between the temperature change in the Antarctic and the rise in atmospheric CO2. Okay, the 800-year lag is well explained by the transit time to propagate a temperature signal through the ocean to those sites where hydrate accumulates. And the production rate, this is an important point, the production rate and storage capacity of those geologic reservoirs, that's an important constraint on the timing of these glacial interglacial events. Okay? Enough time has to take place. There has to be enough time to accumulate sufficient amount of CO2 in these reservoirs so that when a temperature perturbation comes along, it produces the kind of event that punctuated the late Pleistocene. And so, if this hypothesis is correct, it requires a reevaluation, a complete reevaluation of the carbon cycle, because it says that the flux of carbon from these geologic sources is currently completely underestimated in the global carbon budget today. Okay? The global carbon budget today takes estimates from events associated with spreading sites, and those are completely underestimating the amount of carbon that is accumulating in the sediments today. Why is that important? It's important because the ocean is warming today. Okay? And sites where hydrate is stable today are susceptible to the same warming and therefore the same destabilization that has punctuated the last 800,000 years of Earth's history. That's why it's important. Okay, and with that, I'll thank you very much.
Questions?
That was a lot, wasn't it? Yeah.
Yeah. If your hypothesis is right, to which extent would that be applicable to the modern situation, to the current warming?
I'm sorry, could you say it one more time?
If this mechanism,
yeah.
if it is correct, to what extent would it be applicable to the modern
warming? Yeah, that's the perfect question to ask, because that's exactly what people are starting to think about in terms of methane hydrate stability. Okay, so it turns out that, in fact, if I have the time, let me show you a very important observation. Okay, so some of my colleagues are studying just that. Okay, this is a site off Chatham Rise, off the east coast of New Zealand, and this 22,000 square kilometers of the Chatham Rise is punctuated by what are referred to as pockmarks. And some of them are enormous in size, hundreds of kilometers in diameter, okay? And people have puzzled over what causes these things. And they've been attributed to methane hydrate destabilization, okay? But it turns out my colleagues just returned from a cruise to Chatham Rise to investigate whether or not there's methane there. And guess what? No methane. What they do find, however, is a mineral called dawsonite. Dawsonite is a mineral that forms in the presence of CO2. Okay? So these pockmarks may, in fact, be the manifestation of the destabilization of these reservoirs. Okay? what's also important to recognize is that they find horizons where these pockmarks occur at each of the previous interglacial transitions as well. So it's not just these, but it's also during each one of the last glaciations. Now get back to your question. These pockmarks occur all over the oceans. They're found at intermediate water depths in all ocean basins. And people are looking at some of them today that are indeed associated with methane hydrate, and they're becoming unstable. There are places in the Northeast Pacific where pockmarks are being formed today as a consequence of the warming that's taking place at intermediate water depths. That's why it's so important. Okay?
So the scale is comparable to the deglaciation?
Today?
Yes.
Nobody knows. Nobody knows. One of the challenges to this, of course, is to map out, to explore how much of this is out there. We have no idea. No idea. I mean, just 15 years ago, we didn't know liquid CO2 existed in the ocean.
Question?
Yeah.
One idea for getting rid of CO2 from
Yeah.
fossil fuel burning
Right.
would be to put it in the deep ocean.
Right. Yeah.
Maybe
That's right.
such a good idea.
Well, yeah, I mean, we could have a long discussion about that. That has a lot of implications.
Not likely to ever happen, but
I don't think it's likely to happen, and it's not a viable solution. Yeah, but yeah.
I have a question about the PETM.
Yeah.
So I'm coming out from a geologist's perspective here. So right at that time frame is right when you have the closure of the Tethys and the
Yeah.
collision of India with Asia and changing of the ocean
Right.
circulation system.
Yeah.
So what sort of impact, so it doesn't look anything like it would today in
Right.
terms of ocean circulation.
Right.
Dramatically different. Does that get factored into these models like the ZB 26?
The ZB model? Yeah. So the ZB model uses an ocean configuration that looks like the Paleocene-Eocene time interval, okay, with the open Tethys and the closed Drake Passage and so forth, okay? So it's configured to look like the early Cenozoic ocean, okay? And so those the lead lag estimates that come out from that model are a reflection of the transit times that would be associated with ocean circulation at that time. Now, how realistic the ocean circulation is, that's open for discussion, I guess, because you can't validate it against modern observations like we can with the model that I showed you here. But nonetheless, I think they put some reasonable constraints, okay? They give a broad range of possibilities for that lead-lag relationship. But in either case, it only scales between 0.6 and 1.1 petagrams of carbon per year, even in the most rapid case, okay? So it's still 10 times less fast than the perturbation that's taking place today, irregardless of the uncertainties in the ocean circulation.
Okay, Lowell's going to be around the rest of the day and tomorrow, and you'll have other opportunities to meet with him if you have more questions, or you can come up after the lecture. But let's thank him for a very stimulating lecture.
Thank you. Thanks, everybody.